All right, so we're going to finish up our notes from class today. So we're talking about algebraically now. So we did look at some geometric representation of vectors. We know the magnitude of a vector has to do with how long we draw it. So now how do we find the magnitude of a vector algebraically? So first of all, if we have a vector algebraically, we're going to have its component. So we'll say vector u can be written as AB, where A and B are the horizontal and vertical components of our vector if we draw on the xy plane. So the magnitude of that vector, right, how long it is or the size of it, is really just Pythagorean theorem. So the magnitude of u, or the distance it travels, is going to be equal to the square root of a squared plus b squared. Okay? So we're just basically doing Pythagorean theorem again. Excuse me. And what this really comes back to is our polar coordinates. So that is the magnitude of our vector. I'm going to give you a picture to go along with that. So if we have on the xy plane, I'm just going to remind you geometrically what it means. On the xy plane, if we have some vector u, I'll draw it in purple, centered at the origin. So there's our vector u. The components, A would be the horizontal component, B is the vertical component, and to find the length of u, or the magnitude now we're calling it instead of radius, right? In polar we call that the radius, that purple length. Now we're calling it the magnitude of the vector. It's the same thing. We do Pythagorean theorem. Okay, so that's how we find the magnitude algebraically. So let's practice it. Find the magnitude of vector u. Remember, a textbook doesn't use the harpoon, so we have to, I'll add it in whenever we see it here. I might forget, but I'm supposed to add it in. I'm going to pause the video for a second because I need to charge the Apple Pencil. Okay, so we know that I don't need to draw out the geometry of it. I will afterwards. But we know our formula here for magnitude. It's the same thing as finding, so there's our vector u. It's the same thing as finding the radius in polar coordinates. It's the Pythagorean theorem. So it's going to be the horizontal component squared plus the vertical component squared, and then we square root that answer because it's really it's equal to the hypotenuse squared, but we just want the hypotenuse, not the hypotenuse squared. So once again, I'll keep saying we're basically just doing Pythagorean theorem here. So the magnitude of vector u is going to be the square root of 9 plus 16. So that's going to be equal to the square root of 25, which is 5. All right, so that's how long it is. It's 5 units longer. That's the magnitude of the vector. So you're going to try one on your, I could show you algebraically what that means. So again, if I draw this vector in purple, so I'm going to draw my vector in purple again. So if I use the components, I go over 3 in the horizontal direction. I'm just kind of not drawing it perfectly to scale. And then down 4 in the horizontal direction, right? So that's like our 3. These are our components of our vector. I draw it in purple. That means 5 happens to be the magnitude of that vector. So this was what? Vector u again. So vector u, and then we can say that the magnitude of u is equal to 5. Also, I would say that some textbooks, if you look this up online, some textbooks and teachers will use a double bar there to mean magnitude, so that they don't want it really to think of it as absolute value. But I kind of like it like that. So anyway, you're going to pause the video here and see if you can find the magnitude of this vector. And it might help you to draw it as well if you don't remember exactly how to do it algebraically. Okay, welcome back. So I did it, and I got the square root of 26 is the magnitude of vector v. All right, and we would leave it like that. You could turn it to a decimal, but we like the exact value. I'm going to change colors here. Now we're going to talk about the direction angle of a vector. So the direction angle of a vector, we can find its magnitude, and when we draw it geometrically, we can just draw it how we want it to point. But we want to talk about like what angle is that. So again, if we slap this thing on an XY plane, we're going to think of our angle of 0, our like main direction, as being along the x-axis. We just sort of pick that arbitrarily. You saw, as we talked about in the navigation we did today from Spain to North America, that when you're orienteering or you're doing some dead reckoning, we're going to use due north as 0 degrees, our heading due north. But when we're doing math in the pure mathematics, just to make it kind of fit with polar and everything else, we make 0 degrees be the x direction, the positive x-axis direction. So when we want to find the direction angle of a vector algebraically, it's the same thing as finding the angle in polar coordinates. All right, so we're going to say the direction angle of a vector, we're going to say the positive angle, so that's key that we got to choose the positive, between the x-axis and a position vector, or just a vector. I'll call it a position vector for now, is called the direction angle. And of course, in this diagram in general, we'll call it theta. All right, so if we think about a vector, I'm going to look at it geometrically first to figure out how we do this algebraically. We've got our x and y plane, and I'm going to throw a vector on there in purple. If we break it down into its components, its horizontal and vertical components, I'll call this vector u, right? We break it down in its components. We've got A and B representing the horizontal and vertical components. We can write that vector u in terms of its components as A comma B with those pointy brackets. Just to remind you of the other notation, we could say it's A I plus B J. So we can also write it in that notation. All right, so that vector with components A and B, we need the direction angle, and the direction angle is going to be the positive angle between the x-axis, in the positive direction of the x-axis, and our actual vector. So how are we going to find theta if we have A and B? Well, again, it goes back to the geometry, and it's the same thing we did for polar. So we can say that this is direction angle. So I can write my tangent. I was trying to decide what color. I'll just do it in this color. Tangent of theta. Actually, I should stick with it in purple. Tangent of theta is equal to the opposite side, so the B component, divided by the horizontal component, A, and then we solve that for theta. So we arrive at theta, we inverse tangent both sides, equals inverse tangent of the B component of the vector divided by the A component of the vector. So that's how we're going to find algebraically the direction angle of our vector. And of course, A cannot be 0 because we're dividing by A. So let's do an example. Find the direction angle of a vector. So I have my vector in algebraic form as -1, 5. Those are my components. As a reminder, I could call it -I plus 5j, just to get used to that other form. That's if we do scalar multiples of the unit vectors. So to find the direction angle, theta is going to be equal to inverse tangent of the horizontal component, the vertical component divided by the horizontal component. All right, so, and that's going to give us our reference angle. We'll worry about quadrants later. So for our example, we do inverse tangent of 5. We're going to need a calculator for that. And I'm ended up getting, the Apple Pencil died again. Sorry, let me charge it for a minute. So using a calculator, and I inverse tangent in degree mode, I get negative 78.7 degrees. And we're just going to think of that as our reference angle, because the whole inverse tangent thing, we remember that it can only report back angles in quadrant 1 and quadrant 4. And when it's in 4, it's going to report back negative angles. But if we look back at our definition, the direction angle should always be given as a positive angle, not a negative angle. So we can just think of 78.7 as being our reference angle. We can use the components to figure out what quadrant the vector is actually in. So negative 1, 5 means I go over 1 in the I direction, negative 1, and then up 5. If I draw it somewhat to scale, there's our vector v. Negative 1, up 5. So it's in quadrant 2. So our reference angle is 78.7. So that means I know this angle, it's our reference angle, is 78.7 degrees. So we really want our positive angle, our direction angle is our positive angle from the positive x-axis. This part is our direction angle. So you could find it by doing 180 minus 78.7, and we'll get 101.3 degrees is our direction angle for for a vector with these components. All right, so you're gonna try one on your own. Pause the video here, see if you can find the direction angle of that vector. Okay, welcome back. You should get a direction angle of 306.9 degrees. Again, if you're having trouble getting these answers, that's something you definitely want to ask me right when you get to class. Before we even start the practice, make sure you ask me, like, I did something wrong, check my work, I'll look at it for you. Okay? Let's move on to some other things about vectors. So equal vectors just mean they're equal if the actual numbers are the same. So we know what equal vectors means geometrically. They are the same length, and they're going in the same direction. So they're going to be parallel and have their arrows pointed in the same way. I'll say that vector u and vector v here are equal if I actually drew the same length in the same direction. What does it mean, though, algebraically? So let's say vector u, if we break it into its components, is a comma b. That means vector v would also have to be a comma b. All right, so I could say it this way, maybe would be a nicer way to say it. If vector v is cd, I would say that a equals c and b has got to be equal to d for these vectors to be equal. So they have to be the same numbers. It's pretty simple. So again, the point of this is it kind of sucks to do vector operation geometrically. We want to figure out how to do it algebraically. So now we're going to really focus on some heavier operations with algebra. All right, so for vector addition, the actual rule for algebraically, it makes sense. We already talked about it, but I'm going to formalize it here. If one vector u is AB and the other vector v is CD, then the vector u plus vector v will be equal to a plus c, and then the vertical component will be b plus d. You just basically add the horizontals and add the verticals. It makes sense. We're adding vectors, you just add their components. All right, so here's an example. Here's vector u and vector v. How would we add them algebraically? We add their components. So vector u plus vector v equals 2 plus negative 3 for the first set of components, and then negative 7 plus 4 So it's going to be equal to -1 and -3. That is our answer. Let's look algebraically, geometrically how we'd add these. I think it's good to always make the connection. So this is, again, what we were doing. I want to make sure I'm going in the right spot here. This is what we were doing when we were doing our vector voyage. So component-wise, the first vector, vector u says go right 2 units, so that's like about like this, and then down 7 units. So that's like 2, that's like 4, that's like 6, and then maybe that's like 7. So if I draw the result of adding those two components, there is my vector u geometrically. Now, if I want to add vector v to that, I'm going to look at vector v with its components. 1 second. So vector v says its components are -3 in the horizontal, and then up 4. Whoops. So vector v, I'll do that in this like orangish reddish color, is over here, if I just draw it at the origin. So now if I want to combine these or add these vectors together, the way we add vectors geometrically is we take them and we connect them. Oh, didn't grab the whole thing. Let me try that again. We connect them tip to tail when we add vectors. All right, let's get that V out of there. I want to try to grab this red one. So now if I bring this down here and connect it tip to tail, let's see how this worked out. That's how I would add the purple vector and the red vector V. And it seems that I would end up like right here. Sorry that it keeps jumping around. It seems that I would end up here, and if you draw your resultant vector, that should be the vector of adding them. And we said that our vector should be left 1 and down 3, so I'm going to say that that's about right. I go left 1 and down 3. If I drew my vectors exactly to scale on graph paper, it would work out to be in the same spot. So that's how you add vectors geometrically, tip to tail. We already knew that. And we're saying that that's annoying to do. As you can see, I have to translate the vector down, connect it tip to tail. So we're trying to make an algorithm for which we can add vectors algebraically. And of course, it makes sense. We just add the components and we're done. Unfortunately, vector multiplication isn't quite so simple. But for addition, we can do it this way. Sorry, I had a guest visitor. I forget what I was saying, but I think we finished up. I paused the video for quite a while. I think we finished up adding vectors algebraically. So now it's your turn. See if you can add these vectors algebraically. I know it's pretty easy. Take the second to do it and see if you get the right one. Okay, welcome back. I got -4, -2. Thank you. And then, so I want to just remind you of this. I won't put plus, I'll put minus. Of this form also, the IJ form. All right, so there is our other way to express this vector. Action. All right, so now we're going to look at scalar multiplication. So when I said like multiplication is not as easy, multiplying a vector by a vector is not such an easy process algebraically. But scalar multiplication is something different. Remember that scalar means that's just a magnitude, just a number like 5. I'm not actually multiplying a vector times another vector. I'm just taking a vector I already have, like u, and let's define u, because we're doing it algebraically, as its components. So a comma b, we'll break it into its horizontal and vertical components. We're going to just multiply that by some other number, a magnitude, right? So if we say like, if k is a scalar, again, that just really means it's a number, then k times u, the vector u, would be equal to k times, well, let's do it this way. All right, in vector form. It'll be k times each component. What do we think that would do to a vector geometrically, which is interesting? Okay, what do we think it might do to a vector geometrically? So geometrically, what's going to happen is if I have a vector u, and its components are a and b, let's say we double it. by a scalar of 2. We expect that it's going to basically make our vector twice as long. It'll be like 2 of these now, right? And that makes sense because if I double each component, so now it's b and then another b, we're going to end up here, and that makes our vector twice as long. So yeah, it's going to basically multiplying by a factor, a scalar of k, will make our vector twice as long in the direction that it's going. And if you multiply by a number less than 1, it'll actually make it shorter. All right, so that's how scalar multiplication works. Okay, so if the number you're multiplying by, the absolute value of it, is bigger than 1, it's going to increase the length of our vector. If the absolute value of k is less than 1, it's going to decrease the length of our vector. If it's equal to 1, then it doesn't change anything. The length is the same. And if our k is less than 0, not the absolute value, but just if it's less than 0, that means if k is negative. If we multiply by a negative scalar, it may change the length. It will also change the direction. It'll change the length depending on k, if it's bigger than 1 or less than 1. But we're talking about the absolute value of it. But really, just if we multiply by a negative version, it's going to change the direction of our vector. All right, so algebraically, that's how we multiply scalar multiplication. We are not going to, again, multiply a vector times a vector yet today. All right, so we can look at an example. Let's take the vector let's say v is the vector. Its components are 2 and 4. Geometrically, I don't want to do that because it'll run into my writing. I want to erase this one. Let's do it over here. So the vector 2, I go over component 2 and up 4. So here's our vector v. So if I multiply that by a scalar of, like, let's say, what is 2.5 times v, that's going to be equal to 2 times 2.5 is what, 5? Because I multiplied 2 times 2 is 4, plus another half is 5. 4 times 2.5 is 10, I think, right? 8, and then half of that, 10, yes. So 5, 10. Let's look at what happens geometrically. So if I multiply this vector, each component, by 2.5, that means we have a second 2, and then half of another one, because that's 2.5. That's my new component, and again, that's 5, which matches. Then if we take our 4 and we multiply it by once and by another 4, and then by half of a 4, which is a 2, that will make our new vector end up here, which is 5 and then 10. And of course, it wouldn't turn like that. It would be a straight line. And all we really did was we doubled our vector. I didn't draw this exactly to scale, so it doesn't work out perfectly. But the length of that vector just doubled. The magnitude, I should say. Okay? So multiplying a vector times, or I shouldn't say doubled, went by 2.5 times because our scalar was 2.5. So our new vector would be, I'll just draw it over here, going in the same direction. That would be our new vector compared to our original vector, which was like that. It's going in the same direction, but its magnitude is increased by 2.5 times. So it's like lining up 2 of these guys and then like a half of another one. Okay, again, I'm not drawing them perfectly to scale, but you get the idea. So that's what scalar multiplication is. All right, so now we're going to do an example with some other operations, which just happened to our stuff here. Okay. So this is the last kind of thing we're going to do. We can do vector operations algebraically. I'm going to write down a couple things. So if u equals, I'm just kind of summarizing, AB and the vector v are components C, D, we would do vector addition algebraically would be equal to A plus C, adding the components. Vector subtraction would be subtracting the components. Order is going to matter here. A minus B, sorry. And then C minus D. Let me just make sure I have all this in the right order, because order does matter. All right, so I don't subtract A minus B. I'm subtracting A minus C, component minus component, and then B minus D, component minus component. And then I have scalar multiplication. If I take a number k and multiply it, a scalar, by my vector, I'm going to multiply both components. So it would be, I'm multiplying by vector u, so it's going to be k times A and k times B. All right, so there's our three vector operations algebraically. And there are a bunch of properties that hold. There is a special vector we should talk about. We talked about the unit vector. It's 1 unit long. We also have a zero vector, which is 0 units long. And the zero vector will be written as 0, and it is 0, comma 0 are its components. That's a zero vector. So a lot of the algebraic properties of algebra hold. For instance, the commutative property. If I add vector u plus v, that will be the same thing as vector v plus vector u. Okay. Associative property. If I'm adding more than one vector, the order in which I add them does not matter. I can add any two first and then add the resultant vector to the third one. When I'm doing scalar multiplication, if I had two scalars that I want to multiply by, the order in which I do that doesn't matter. I can multiply the scalars first and then multiply them by the vector. Or I can multiply one scalar by the vector, take the resultant, and multiply it by the next scalar. Distributive property holds for scalar multiplication. So I have k times the addition or the sum of two vectors. I can multiply the scalar to each vector and then add those results. That's another property, the distributive property that holds. Some other ones. The 0 times any vector gives you the 0 vector. Okay? 1 times any vector, the scalar 1 times any vector gives you back it's the same vector. So 1 is still the multiplicative identity. Negative 1 times any vector will give you back the same vector but in the opposite direction. So it'll have the same magnitude but opposite direction. And then adding a vector to its opposite vector, okay, will still give you the 0 vector, or give you 0. So all right, let's do an example and then we'll be done here. So let's see. I think this is example 4 it would be. Actually, we don't need to. I think you get some of this. We're going to do the examples in class, so this video is getting long enough. We'll cut it here. So we'll talk about the next example in class, and we're just going to do some practice on Friday.